Angiotensin II is initially derived from the 453 amino acid protein called angiotensinogen, which is constitutively secreted by the liver. Next, renin, an enzyme secreted by the granular cells within the kidney, cleaves the first 12 amino acids from the rest of the angiotensinogen protein. This 12 amino acid peptide is now referred to as angiotensin I. Soon after angiotensin I is cleaved from the angiotensinogen protein, the angiotensin-converting enzyme, or ACE, which is constitutively secreted by the lungs, cleaves 4 of the last 12 amino acids from angiotensin I, leaving us with the first 8 amino acids, which is referred to as angiotensin II. Now, the rate-limiting step in this series of reactions is the abundance of renin. Angiotensin II regulates GFR by regulating renal plasma flow and the filtration coefficient. We'll use this graph of renal plasma flow and GFR as well as the image of the glomerulus to explain. See, angiotensin II decreases GFR by promoting the vasoconstriction of the afferent and efferent arterioles, which reduces renal plasma flow, which automatically leads to a reduction in GFR. Now, once angiotensin II is removed, afferent and efferent resistance return to normal, as does renal plasma flow and GFR. Angiotensin II also regulates GFR by influencing the filtration coefficient. It does this by promoting the contraction of the intraglomerular mesangial cells, which leads to a reduction in the glomerular capillary surface area, which results in a reduction in GFR. How does angiotensin II promote afferent and efferent arterial vasoconstriction as well as intraglomerular mesangial cell contraction? Let's use this illustration of a cell to explain. Vasoconstriction or contraction starts when angiotensin II or AT2 binds the angiotensin type 1 or AT1 receptor. The AT1 receptor belongs to the family of G protein coupled receptors, which work by activating different small g proteins. In this case, binding of AT2 to the AT1 receptor activates the small GQ protein, which activates the enzyme phospholipase C, or PLC. This in turn leads to the production of 2 important signaling molecules known as diacylglycerol, or DAG, and inositol triphosphate, or IP3, from the precursor molecule phosphatidylinositol 4,5-bisphosphate, or just PIP2. Now, through a series of additional steps, DAG and IP3 promote the release of intracellular calcium, which leads to an increase in intracellular calcium. Once released, calcium promptly binds the actin polymers and promotes contraction of the myofilaments, which results in the vasoconstriction of the afferent and efferent arterioles, as well as the contraction of the intraglomerular mesangial cells, both of which result in a reduction of GFR.